Hey guys, today we're going to be looking at thermodynamics. You have your graphic organizer, so go ahead and copy along. All right, here we go. So thermodynamics is a field of study where we're going to be looking at whether or not a chemical reaction is spontaneous. Another word for spontaneous is thermodynamically favorable. Now, when you hear thermodynamic favorability, or spontaneity or spontaneous, it's not referring to how fast the chemical reaction is occurring, but rather if the reaction will occur without an outside intervention. So thermodynamic favorability refers once again to a process or reaction that occurs without any outside intervention. So if I were to take a ball to the top of a hill and let go, that ball is going to roll down. However, a process that is spontaneous or thermodynamically favorable in one direction is not going to be in the reverse direction. That ball will never roll back up the hill on its own. There has to be some sort of outside intervention. Me picking up that ball and taking it to the top of the hill would be an example of that. So when we're talking about thermodynamic favorability, we need to understand what entropy is. And I laugh because entropy, very obviously, is abbreviated by the letter S. I don't ask me. I wasn't there when they made these letters. Entropy is a measure of the randomness or disorder of a system. The more chaotic it is, the more random, the more disordered, the higher its entropy. And the more ordered it is, the less entropy it has. So I want you to think about the three states of matter: solids, liquids, and gases. Which ones have the greatest disorder? Which ones have the least? If you're thinking that gases have the most disorder and solids have the least, you'd be correct. The more random or disordered, the higher the entropy. So therefore, gases are going to be highest in entropy, whereas solids are going to be lower. Once again, when we're looking at chemical reactions or processes, it's important to understand these states of matter because we can use these to help predict the sign change for delta S. As a substance dissolves into water, their entropy usually increases as well. So for example, if I were to look at this chemical reaction here, calcium oxide, which is a solid ionic compound, plus, carbon dioxide, which is a gas, this will turn into calcium carbonate. Because I'm starting with a solid and a gas, this gas right here is very high in entropy. I do not have any gases on the product side, so this tells me that this is becoming more ordered. And therefore, the sign for delta S for this reaction should be negative, right? It's getting more ordered or more compact. Those carbon dioxide molecules are adding to the calcium oxide. On the flip side, if I were to go ahead and take something like water in the solid state and melt it into water in the liquid state, solids are more ordered than liquids are, or liquids are more chaotic than solids are. So the change in entropy for this reaction would be positive. And I do expect you all to be able to predict these sign changes for the chemical reactions. Last but not least, when we're talking about entropy change, I also want you to note that a system's entropy will increase if the products contain more particles than the reactants. You should still look at the states of matter first. That is more important. However, if there are just more particles on the product than the reactant side, then entropy is going to go ahead and increase. A system's entropy will increase if the system's state changes to a higher entropic state. This is what I was saying earlier regarding solids to liquids, liquids to gases. So go ahead and take a moment here to determine the sign changes for the following reactions. Oh, I just noticed here, this is a gas. That is important for this one. Take a moment and pause the video. All right. So if I check out this chemical reaction here, it starts as a solid, ends as a solid and a gas. Since I produced a gas, this is more has greater entropy, and therefore delta S will be positive. Let's jump down to this third one here. Same idea, solid and gas, or excuse me, gas to solid. This chemical reaction is decreasing in entropy because solids have less chaos, less randomness. So when we look at this chemical reaction, we see that all the states of matter are gases. So I can't use the gas to solid to liquid idea. What I can do is look at the number of particles. I'm starting with 4 particles and ending with 2. Since I end on the product side with less particles, this means that the entropy is decreasing. It's less chaotic and less disordered. 4 particles is way more random than 2 particles is, so therefore the entropy change will be negative. It decreases in entropy. All right, so why do we need to understand this? Like, what's going on with entropy, and how does this tell us about thermodynamic favorability? This all has to do with the second law of thermodynamics. The second law of thermodynamics states the following: the entropy of the universe is always increasing. That means whenever I look at a chemical reaction or process, the entropy of the universe must go up. If the entropy for the universe is not increasing, that reaction cannot occur. This is a law. This is just something that we observe to happen whenever a process or reaction occurs. Once again, the second law of thermodynamics states that the entropy of the universe is always increasing. When a reaction occurs, the entropy of the universe goes up. So the question I always like to ask my students is this: what is the entropy sign, for this reaction? This reaction here is water freezing. Liquid to solid, water freezing. Well, the entropy for this reaction is going to be negative. Is this breaking the second law of thermodynamics? And the answer is no. This chemical reaction is not the universe. The second law of thermodynamics states that a reaction or process must increase the entropy for the universe. This is just the system. Remember, the universe is composed of the system and the surrounding. So the entropy of the system plus the entropy of the surrounding will equal the entropy of the universe. And therefore, when I look at this process here, even though delta S for the system was negative, water can freeze because the surroundings entropy will go up. When we are studying, while we are studying this system and not the universe, we can say that most reactions do increase in entropy. So this is a less common example because delta S was negative. Most reactions will have a positive value for delta S because this increases the value for the entropy of the universe. So let's make all of this kind of come together. We started this unit by talking about enthalpy. Yes, enthalpy, H, not entropy, S. Enthalpy does help us understand a little bit about spontaneity and thermodynamic favorability. Most reactions are exothermic. The reason this is because when an exothermic reaction occurs, it releases energy to the surrounding. When the particles in the surrounding are moving faster, the entropy for the surrounding goes up. And if we kind of go back to our equation here, where it was the system plus the surrounding equals the universe, enthalpy is going to be focusing on this part because an exothermic reaction releases heat energy and makes the particles in the surrounding more chaotic. So therefore, a negative delta H makes the S for the surrounding positive. Energy is released to the surrounding, causing the surroundings entropy to go up. So let's take a moment here to kind of review what we've talked about today. We know that most reactions are exothermic. The reactions that are exothermic tend to be favorable. This is when delta H is negative. Remember, negative. The reason that delta H being negative makes for a thermodynamic favorable reaction is because it increases the entropy of the surrounding. Most reactions that increase the entropy are favorable. So entropy, remember, is chaos, randomness, or disorder. With a positive delta S, this is more than likely going to be favorable. Now, these are two separate thermodynamic values for a reaction. So, in the scenario that I have an exothermic reaction whose delta S is also positive, this will always be thermodynamically favorable. This will never not be. Gotta love those double negatives. If a reaction has a positive delta S and a negative delta H, then it is always thermodynamically favorable. We'll spend some time talking more about this when I come back. If you have any questions, feel free to shoot me an email. Thanks so much. Have a great day.